Hello guys, good afternoon, good evening, or maybe good morning for some people. My name is Thiago Souza. I'm from Brazil. I'm a civil engineer in Latin America area. And today, it's very special for us. Dr. Marcos Arroyo will speak for Geotecnia Brasil channel. But before I introduce Dr. Arroyo, I will give some information in Portuguese and in Spanish, ok? Caros amigos, boa tarde a todos. Para algumas pessoas, talvez seja boa noite, ou até mesmo bom dia. Eu não preciso mencionar meu nome, porque boa parte dos colegas já conhecem. E hoje é um dia especial. Hoje teremos uma palestra do professor Dr. Marcos Arroyo, ele que é uma autoridade em análises numéricas e todo espectro da geotecnia, se prontificou a gentilmente falar para nós. E, coincidentemente, essa é uma semana onde completou-se 3 anos da tragédia de Brumadinho. E nós temos, antes de tudo, a missão de, mais uma vez, deixar nossos votos de solidariedade aos familiares, amigos que perderam entes queridos. E a nossa contribuição é de trazer um pouco da técnica, e nada melhor do que chamar uma pessoa com gabarito. Muito buenas tardes a todos, buenas noches. Eu sou Thiago Souza, eu sou de Brasil. Antes de todo, me gostaria de fazer um agradecimento a todas as pessoas que estão com nós outros. É muito chévere ter muitas pessoas de Brasil e outros países, e agradeço às entidades que estão com nós outros, agradeço a toda a equipe de Geotecnia Brasil, e quizás eu creio que nós outros vamos atender uma conferência muito especial com o professor Marcos Arroyo. Eu vou falar em inglês agora, ok? E me gostaria de dizer também que depois da apresentação vamos ter uma sessão de perguntas, respostas, e muitas graças por a participação de todos, ok? Now I would like to call Dr. Marcos, please. Marcos, thanks again for your participation here. Marcos is a civil engineer. He is PhD from Bristol University, with a thesis on the interpretation of laboratory seismic tests. Nowadays, his job is in Polytechnic University in Barcelona, and he gives some courses like geotechnical design, offshore foundation, and marine geodynamics. Today, Marcos will explain some information about computational analysis of Brumadinho Tailing Dam. In November 2019, a team led by Marcos Arroyo was designated by the Public Prosecutor Office of Brazil, Ministério Público, to perform numerical modeling of the Brumadinho Tailing Dams, so as to clarify the proximate cause of the abrupt failure. You can check the report in internet, all right? And I would like to say thanks for Marcos Arroyo for a good job. And Marcos, please, you can start your presentation. You can speak in English or Spanish. It is up to you, all right? But if you speak in Spanish, please speak slow, because people from Brazil don't speak Spanish. Some people from Brazil don't speak Spanish, okay? Tem que seguir Marcos, and now you can start your presentation.
Thank you very much, Tiago. I am humbled and honored by being here at Geotecnia Brasil. Can you, I assume that you can see my screen, no? Can you see my screen? Please say something.
Yes, go ahead, Marcos.
Okay. And now it's in presentation mode. Well, as I said, this is really something important for me and for the team, because I have the wrong date, excuse me, because today is the 25th. And you know, as you mentioned before, Brumadinho failed 3 years ago. And well, both myself and other people, of course, from CIMNE and UPC. CIMNE is a research institute associated to UPC here in Barcelona. Well, when we were offered the opportunity by the Ministerio Público Federal to dig a bit into this problem, well, we were at the same time were very interested and humbled, because it was a shock for everyone that was attentive to geotechnics. How can a thing like that happen? No? This is the team, and well, it was led by Professor Jens and myself, people from CIMNE. We had the opportunity just before the pandemic to have the visit here at Barcelona of this Leonardo Macedo, an engineer from the police, that he introduces us to the whole complicated data that surround the case of Brumadinho. And then during the process, we had also support from a number of people outside CIMNE. These two are particularly important: Miguel Manica from Mexico and Professor Viana da Fonseca from Porto. Initially, our task was going to be just numerical, but then it did, well, there was a mission creep. We had to do also some tests. So, as I said, this was commissioned by the Ministerio Público Federal to help them to understand what happened on that fateful day 3 years ago. And it was commissioned by the MPF, but it was financed by Vale through an agreement that Vale and the MPF had. We were selected, I think that mostly because they were looking for someone technically competent, but also someone that had been not involved previously in Brazilian mining. And the focus of the project was on the proximate cause of failure. Why that day this thing happened? There are many, of course. If that dam hadn't been there, if that dam wouldn't have been the way it was. But those are not the proximate causes. We were tasked to investigate the immediate cause of failure, the trigger. And there were some conditions to this study. One is that it was going to be taxis-based. And the idea of that was that praxis is very widely spread around the community. So if we could do something useful, that will facilitate dissemination. The study started, and 3 months into the study, we were in the middle of the pandemic. So that, of course, delayed the study. I mean, we were, at least during the first several months of the pandemic, we were not sick ourselves, but it was difficult to work or to start working in that separate mode. No? And after the study was concluded, and that was also a condition, it had to be reviewed by external peers. One of the external peers is here today, Professor Alberto Sayao, that you all know, and the other was Professor Tersariol from Argentina. And then another condition that was not in the contract, but that was a fact, is that shortly after we started with this study, there was another, and there were more, but there was at least another review that came out, which was a review panel that reported within the year of failure, and that had already posited some explanation. An explanation that had two items. One was creep, and the other was suction loss due to intense rainfall. So that was a very valuable study from a number of reasons, but you will see that in that, when we focus on the explanation, we were not totally convinced, and our study was not in any circumstance thought as a rebuttal of this, but of course we had to take into account what had been said. So I will give you a bit of background on Dam 1, and then I will describe briefly the material characterization that was done to as a necessary input for the analysis, and then I will describe the simulations briefly, and then conclude. So, you know very well where the Brumadinho mine was, and it was a medium-sized mine, not very far from Belo Horizonte, and had been in operations for 40 years. From roughly 76 to 2016. And in 2016, the mine had switched to a dry stack operation, so this dam was not necessary anymore and was closed. So at closure, the dam was about 85 meters high, and it was about 700 meters if you go along the crown. So it was relatively large. And when you look at the profile, of course, this had been an upstream dam, except in one occasion where they did something else, but during most of its history had been grown with the upstream method. And the final geometry is, it was relatively steep, no? Because you have roughly 1 to 3 considering the final geometry, and it had this peculiarity, the setback, because initially, up to the mid-90s, these first racings, they were even steeper than the 1-3, and then at some point they started to see a seepage, and they decided it was better to push back a bit the subsequent races. And one important thing is that on this whole area, all these initial stages, it's not that they didn't have any drainage feature in the documentation that is left, but what appears very clear is that even if they had some drainage features, they didn't work very well or at all. So in all this lower part of the dam, there was very poor drainage. That is the racing history of Dam B1. This is when Vale took over, because you know very well also that this dam had been in operation for 30 years before or more before Vale took over the mine. This is when the setback took place, and this is where the first CPTU campaign took place. And this is the second, this is closer. And this is the third one that was shortly before failure. And I'm putting there the CPTU campaigns because the CPTU is what gave the most direct evidence that that was a dam in which there was a lot of material that could be potentially liquefied. But by the time that was done, the dam was already 75 meters high. after closure, what was done in terms of the dam was a number of positive things. The pool was, you see here is the pool shortly before closure, well, was practically completely drained, and all the runoff control measures around the dam and in the front, they were improved and perfected. So water from any storm will be diverted away from the dam. So, and that was working up to a point, no? I mean, when you look at the dam, of course, was heavily instrumented. There were, I think, about 100 between piezometers and water level indicators. It is true that most of them were not, they didn't have a continuous record, but at least, you know, there were 25 that had very good continuous records since closure. And when you look at the piezometric data from that period after closure, well, you see that, generally speaking, the situation was improving. I mean, the water levels in the dam were, little by little, were going down very slowly. So this is one reason why this an explanation based on suction laws was not really, well, when we heard it, something was wrong with that. And then we did look also at the rain gauge. That was there was a rain gauge at the dam. It was not the best rain gauge, but you have registers monthly and daily, I think, not hour by hour, but daily. And if you, and that gauge had records since the beginning, since 1975. If you look at the average yearly rain, well, it is not probably like this year. I mean, the last years before failure were about the driest ones on average on record. So it is, that seems a bit strange. That rain is going to be one of the culprits when you are actually following two of the driest years. What was going on in terms of engineering activity? Well, you know that, and that is not something that we were tasked with. I mean, there were people in charge of the dam, and they were doing the kind of analysis that you do, which is limit equilibrium, and they had some results. And I'm not entering into if are these results correct or not. But for instance, you see for a unknown trigger, they had this hypothesis in which, well, they were coming with safety factors that, however you look at them, were at least suboptimal. So everyone, my impression, was aware that the situation of this dam was suboptimal. And a remining operation was being planned. And what was to improve that situation, the ideas that were discussed were, well, let's improve drainage. And also, well, if you remind the dam, well, the problem disappears, but reminding is going to be complicated, so we need more data and better data on the dam and better instruments, no? So in that last year, the idea is, well, we're going to improve drainage, and we're going to do more site investigation and instrumentation. And those ideas were tested with a top quality review panel that Vale had. And they did sort of okay then, because they did seem the natural thing to do. But those were probably easier said than done, particularly the improved drainage bit. Because the first idea that was attempted was to install deep horizontal drains, 100-meter long, 30 of them, like perforations, you know, at the here on the setback, at the low point of the setback, and here at the lower part of the dam, where it was very clear that the drainage needed to be improved. and 30 were planned, and the desired outflow of those drains would have been 100 meter cubic per hour. And only 14 were installed, and they were shorter, and they didn't drain very much. So that was not a success. And it was not a success, and also it was interrupted abruptly because something that happened 6 months before failure, which was during one of these perforations. Remember, you're perforating silts below the water table with a significant head. So that is always difficult. And one of them sort of, well, during one perforation, there was a blow up at several points in the dams. Some piezometers jumped, so the operation, which was done with aided by pressure, because you need pressure, was halted, and well, and everything was stopped. And later, and this is a very good finding of the expert panel review, they did examine in detail the seismic trace of that event in June, this one, and then the seismic trace of the fateful day of 3 years ago when the dam failed, and the beginning of the failure, which is a beginning that if you time it with the image, the bit that happens before you actually see the failure on the video, it has the same kind of signature, of seismic signature, than that thing that happened in June. So an interpretation for what happened during that drain installation is something like contained liquefaction. But it was contained. It was contained. And during, we will see it, during the next 8 months, there was increasing vigilance, but nothing happened. Nothing happened. The only thing what happened was that they were installing more piezometers, better piezometers, some inclinometers, and they doing site investigation on top of the dam. It is true that that last site investigation campaign included some of the deeper boreholes that were ever performed in the dam. There had been many boreholes in the dam, but the deeper ones were those that just preceded failure. And those deep boreholes were being drilled using wireline and using water circulation. And that was a machine that didn't have a record of, they didn't have a measurement while drilling, and the control of the injection fluid was by hand. They were using this kind of up and down, and that was at the discretion of the operator. And what about the instrumentation? Apart from the piezometers, there were, in fact, there were a number of monuments of topographic well, references, not on top, but just on the stage, just below the top of the dam. You see, and that well, the measurements from that topography, they were a bit noisy because I mean the reference base had been changed a couple of times in the last 3 years before well, since closure. But I think that you can clean that, and when you can, and after cleaning that, what you see is well, really not much happening. Not much happening. I mean, those are very small motions. This is 1 centimeter, no, and this is 2 centimeters. Not much happening until a particular period, which is when the deep horizontal drain were installed. And that is interesting because initially it seems that they were perforating those drains without enough pressure. So there was a bit of material loss through in the perforation. And you can see that, a bit of settlement at the top of the dam because you're losing material through your perforations. And then well, they decided, well, we cannot really keep on losing material during the perforation, so we're going to increase the pressure. And by increasing the pressure, they sort of, the motion of those points, it inverts. So they start moving a bit upwards, no? And then there is the day in which that blow up, that contained liquefaction takes place, and sudden settlement follows. Okay, so all this is very intriguing and interesting, but all that happens 6 months before failure. And as I said, it was contained, there was no water, again coming from there, and during these 6 months, well, those monuments register nothing. Nothing is happening. I mean, the inspections were everybody was looking at that, and nothing was happening. And, well, what about the satellites? You will have heard many things about satellites. By the time we did finish with our report, there were already like 6 studies on the public domain, and we did look at them. And I think this is the one that I found more thorough, by Holden et al. And they have essentially what they say, and that is in agreement also with the expert panel review, is that what the satellites, the INSAR is telling you from the face of the dam, where you will expect some precursor of failure, is just too noisy. There is no clear signal at the face. It is different at the rear. At the rear, you can see consolidation taking place at the back of the dam where the slimes were. But failure 3 years ago didn't take place at the rear. Failure, I'm not going to repeat the videos, I mean, I'm sure that you look at them. But initially, it pushed forward from the front. And there is another video, when you look at it from the rear, you can see that there is a vertical motion at the crest that very quickly extends throughout the crest, and then if you continue, the video comes towards the camera. No? It's in those dramatic minutes. So, if you want to do some numerical analysis, you need to have input. You need to describe the material. And as I explained, the most likely failure was something going through the tailings. There were other materials, but the failure didn't went through the foundation soils, which were strong, and all those materials were not very interesting in terms of the failure. So I'm going just to talk about the tailings. And at the rear of the dam, there is a distinction. You have slimes, which have some plasticity and have a substantial clay fraction. And those did fail, but they failed after the initial failure took place. So they did contribute to the mudslide, but there was only after the tailings at the front had failed. And what was the data on the tailings? There was a lot of historic data, but there were many samples, but most of them were shallow and they were relatively poor quality. And more important is that the testing that had been done with these very numerous samples was unsystematic. It was not guided by theory. So for instance, there was no critical state line of those tailings before a failure. Then came the panel review, and that was different. Those were good quality samples, only they were all a bit too close together. Too close together in one corner of the remains of the dam. And those red points is the places where our colleagues from FIUP and the Ministerio Público went on to take samples for us. And we wanted samples and we wanted tests because in the results of the panel, which were systematically tested, there were some significant gaps. For instance, there was no systematic data on the strain rate effect, and that was very annoying because a creep was postulated as one important thing there. So we needed data on that. And also, surprisingly, there were relatively few tests on contractive, few and drain tests on contractive tailings. So there were things to do. And here is Professor Viana and the people from the MPF, and they were brave. They were deep in the dam, and they took a lot of samples. And when you look at those samples, well, yeah, here you have different samples of Brumadinho tailings, and you have what was called the Preto, and what was called, for obvious reasons, the Castaño and the Vermelho. And you see how these laminations and the scale of these laminations makes that if you test any single of these samples, they are going to be different from one another. So you won't be able to create a coherent picture. So to understand the mechanics of this, it was inevitable to try and reconstitute, to homogenize, create some artificial material. So what we did at the lab is, apart from testing some intact samples, that was done as well, but what most of the work was done on material reconstituted, and they did carefully separate by color. You see, the Preto, the Vermelho, the Castaño. And here you have the grains of distribution of the Preto, the Vermelho, the Castaño, you see. And when the first time I look at this, I say, well, maybe that is not such a good idea, because they seem very similar. Of course, all the tailings there are essentially silts. But you have sandy silt, silty sand, so the panel had been did the same, and they selected their reconstituted materials by their D50. So they could sort of span the different grain sands distributions. We did not do the same in that respect. We did the same in how you test, which is you use moist stamping and then triaxial testing with your moist stamping specimens. But we did look at different properties. For instance, the specific weight. This is the single most peculiar thing of the tailings of Brumadinho. They are super heavy. It was a large proportion of the tailings were iron. This is what remining was a good idea. And you see, I mean, 5 to 4 specific weight. This is outside the range of most soils. And those are our three, you see the Vermelho, the Castaño, the Preto, no? And it was good because color was a good indicator of weight. So we could span all the weight range, which it didn't happen if you select your material by D50. And when we started testing and look at the key properties, for instance, how does it respond when it is shear and drain? Well, a large number of the samples of these different materials show this kind of response, which is described as very brittle. Very brittle, that means that from a peak and drain resistance, you will go, well, to the limit of your testing equipment, to 0. If you look on effective stresses, if you look at the effective stress envelope, this is your friction angle. Well, your critical state friction angle for Brumadinho is here, the blue and the orange. It's not very different from that of other tailings, and it's not particularly low. It's 34, 35. And all those different Preto, Vermelho, etc., they were behaving pretty much the same from this point of view. They were different, on the other hand, when you look at the critical state line on the compression plane. This is a critical state line on the compression plane, and there was significant variation from one material to another. Another message that was interesting from the lab testing was that the peak and drain strength was very different if you were testing after an isotropic, that is K0 consolidation, or after isotropic consolidation. So, and this is the one that is more relevant for in situ conditions, because in situ conditions you will have K0 conditions. So because you will have a larger peak, and the residual strengths of these two series are not very different, this material is more brittle. It falls from a higher strength to an equally low value. You see, this is I'm plotting here. This is the normalized and drained residual against normalized and drained peak. This group here, higher peak, is anisotropically consolidated. Those are the field symbols. Those are isotropically consolidated. And the color represents the material. And well, you might argue that red is stronger in residual, but not really. When you look at the test, those weren't really pushed to the limit of the equipment. But still, there might be some difference between some of them. Still, another interesting point was that we did test systematically to look out for strain rate effects, to see if creep was a reasonable possibility. We were skeptical of that because, you know, Brumadinho tailings are not plastic. And the one message that from our background in geotechnics we had is that expect creep on plastic materials. Those weren't plastic, so why they were creeping? Anyway, we did test for that. And Brumadinho tailings were very rate insensitive. So that was in the lab. But also you have the field results when the dam was intact. And there was about 1 kilometer of CPTU data. 1 kilometer is a lot of data points. And most of them were in the tailings, of course. And they were a bit all over the place, but you could see that there was a lot around here and another group here. So we tried to distinguish two types of CPTU materials. One thing also that struck us when looking at the CPTU was that if you plot the estimations of where the stages of filling on those CPTU profiles, sometimes, I mean, all this variability that you see, well, it appears to be less random. It can be related to a change in stage and the way the dam was built using spigoting and widely spaced. So that left a trace. So one stage might be different from the next at a particular location. No? Back to the Robertson chart. I mean, we distinguish two kinds of data points. Data points that we will call CPTU fine, and others that we will call CPTU coarse. The distinction between CPTU fine and coarse was made by looking at this parameter BQ, which is the normalized pore pressure that you measure on the CPTU. If when doing a CPTU, you're not generating excess pore pressure, that means that that material drains very quickly. And this is what we will call CPTU coarse. CPTU coarse is the blue material here. If you generate more or less, but at least some pore pressure when tested by the CPTU, your material is your tailings are relatively fine, and those are the ones that we plot here in orange. And once you separate between fine and coarse for the CPTU, for the behavior of the CPTU, then you can start looking at their stats separately. And for instance, it was very clear that the conditions for those fine CPTU materials were catastrophic. They had state parameters of, on average, 0.1, whereas the others were on the limit of being liquefiable. You can say, oh no, well, it's just the 82%. But if you believe, as I do, on the work of Bean and Jefferies, they have said that you should select your characteristic value at 85%. So it's very close to the limit, even for the coarse ones. So the coarse ones were really borderline, and the fine ones were catastrophic. So now, where were the cores and where were the fines in the dam? This is the key to create your model of the dam. So how we went on about that? Well, we divided the dam into several sections, you see, that will be later projected into numerical models, and several alignments. And the number of alignments that we introduced was dictated by the number of CPTUs that we have. So we have more or less the same amount of information within a particular block. A block is a section between two alignments and around a section, and also a section that corresponds in vertical to a particular stage of or raising of alteamiento. So once we have this three-dimensional block model, we can compute, based on CPTU, what is the percent of these very bad materials that are in a particular block. And you see there were some blocks close to the front of the dam in which there were very little presence of fines. But there were others that were mostly CPTU fines. Those were looking bad. And there were others in between. How do you translate that into numerical modeling? Well, that is a very good question. And after some thinking, we came with this answer, which by no means might be definite. We decided if you are a block that has less than 10% of CPTU fines, we will call you coarse in our numerical analysis. If you are a block that has more than 50% CPTU fines, we will call you fine in our numerical analysis. At the rear, there are the lines, but those do not intervene in the failure. And everything in between is what we call a mixture. So we have three kinds of tailings material in our numerical models. Before I go to the numerical models, just let me say that another thing which we disagreed with the previous report was on the relevance of bonding for this material. They present a number of arguments. I cannot go in detail through all of them, but to me the definite argument against any bonding on the Brumadinho tailings was given by looking at the in situ testing and fitting this hardening in situ testing of shear wave velocity. No? And you know, shear wave velocity in soils depends on the stress level. And how it depends on the stress level, how is given by this coefficient beta, and how fast it travels is given by this coefficient alpha. And this is an expression that comes from Harding-Arnevich and is very well known. But what is less known is that these two parameters, beta and alpha, they are related, empirically related. We don't know exactly why they are related. But there is a beautiful database that has been compiled by Professor Santamarina and co-workers. Against, you can plot your results there. And you see, this is where Brumadinho plots, which is between sands and clays, as you will expect for a dam of silts, and very far away from the really cemented materials. In cemented materials, you have very little dependence on the stress level of your shear wave velocity, and they are very far away. So no bonding there. Okay, now let's move to the simulation. To the simulation, apart from an idea of where are the different materials, you need a material model, a numerical description of the behavior. And the one that we are using, because we were familiar with, and also because we could put it in practice easily, is CASMA. And CASMA was, it's a brainchild of HiCU, and then it has been adopted by many people, including us. And it can reduce to CAM-clay, and interestingly, it incorporates the idea of state parameter, and of course, is based, as everything that follows from CAM-clay, is based on critical state. And it's relatively simple. And also, interesting for us, when it was proposed, among other things, to model static liquefaction. And it could be extended, for instance, very easily, and we did that specifically for the analysis of Brumadinho, to consider creep, moving it from being an elastoplastic model into a viscoplastic model. When you add creep to CASMA, it still predicts a static liquefaction. You see, you go through a peak and then you fall to the critical state in undrained condition. But interestingly, the peak through which you go, the height of the peak, depends on how viscous you are. Or rather, if you are viscous, the size of the peak depends on how fast you load. If you load very fast, you're going to have a larger peak strength. If you load very slow, you're going to have a smaller peak strength. So this is CASM-VISCO in a nutshell for you. CASM is good, but it's not a panacea. It has some limitations, and you need to understand the limitations when you're using for a case like that. And one important limitation in this case is that CASM doesn't include strain-induced fabric. So what happens is that CASM cannot make a difference between something that has been consolidated isotropically, like here, and something that has been anisotropically consolidated. You get the same peak and the same residual, essentially. So, because we knew from the lab that that was not the case, and that there was a difference in the lab, we had to use for calibration only the anisotropically consolidated results from the lab, because the isotropically consolidated will have misled us. Also, CASM is not good for cyclic loading, but we're working on that. CASM has a few parameters. Some of them are related to critical state line, or they are well known from other models. Then there are state parameters like over-consolidation and the state parameter. And then there are some that are a bit more strange. Those more strange, for the case of normally consolidated tailings, similar to Brumadinho, you can get around those more strange parameters and substitute them by something that will be simpler to measure, like the normalized undrained strength or K0. And that has been explained recently using another case, Marius Proof. But anyway, even if those things you can get from in-situ testing, you will have to get something from the lab, the critical state lines. And well, I mean, that poses the question, because we were dividing the dam into CP2 fine, CP2 coarse, and those were, well, based on field testing, how we were going to relate that with the reconstituted information, with the information from reconstituted materials that was being obtained at the lab. Well, we did use permeability to relate field and lab. And the key is that you can evaluate permeability from grain size distribution, for instance, and this is for our reconstituted materials and all the samples of Brumadinho. No? And also you can input permeability to a model that uses CASM, the same parameters that you're calibrating, and you're predicting the BQ on a cone penetration. let me just show you how that is done. I mean, that is done because you need some relatively advanced numerics. You cannot do that with classes, but give them a couple of years and probably you will. And anyway, if you simulate your cone with the same material model, you can figure out what is the BQ, how that BQ depends on permeability. And therefore you can say, okay, well, if the BQs that I'm saying my fine materials in the field they are above this limit, then they have to be the ones with permeabilities less than 10 minus 6, say, 10 minus 6 or 10 minus 5, no? This middle. So, well, probably the brown, the castaño will be the one more similar, no? And that kind of reasoning was applied to try to go from the lab to the field and back. So after you go through all that, you have a model that you can compute. You have a distribution of materials and you have parameters for the materials. And well, let's see the simulations. We did two kinds of simulations. Ones are what we call the reference models, and those are plane strain models. They are 2D, different sections of the dam. It is true that if you look at the failure in this central section, well, it looks initially a reasonable approximation. That is, it is like very 2D. It falls very homogeneously. So, and then in this particular section, we will pay attention because this is where the last boreholes were being drilled. So we have our materials, section 1, section 2, section 3. You see the distribution of red, yellow, and green corresponds to red is a fine CP2 tailings dominate. And green is the opposite, yellow in between. No, it changes from section to section. Also, it changes from section to section the geometry, for instance, of the contact and the racings. No, and section 3 is the one that had a more unfortunate geometry, I would say. Of course, you have to also give properties to all the other materials, but I won't go into that. I will also mention that the simulations that we carried out were a couple hydromechanical simulations. So we needed also flow properties, permeability, retention curves for the unsaturated section, the section that will dry or get wet in contact with the atmosphere. And for that, we did rely very much on the work done by the previous review, by the review led by Robertson, which in this respect was very useful. So once you're done with that, you start building your models with all the phases, raising, filling, raising, filling. All this is done with a CASMA, and you're building and consolidating simultaneously. And the first key check here is that you need to have a model that allows you to build the dam. The dam was built and was stable for 3 years before failing. So you need to have properties that allow this to happen. And that happened in the 3 sections. We were able to build the dam on the 3 sections. I should mention that as the dam is raised, you see you're using hydraulic boundary conditions given, for instance, by the extent of the pool in the dam that was known from historical records. And then where you don't have the pool, we were applying precipitation during construction, just the average rainfall for all history. And after construction, we did test 2 ideas. One, what actually happened, which was that it was relatively dry. And then what we call the wet variant. What will have happened if after construction you have 3 years of a lot of rain, which didn't happen, but just in case. Anyway, after, in the 3 years after closure, what the models give you is, for instance, significant settlement at the rear on the slimes, and almost nothing happening at the front. And that is exactly what you will, what the INSAR gave. The INSAR gave about, say, 70 centimeters here at the rear. And in the simulations, we get about 65, which, considering we didn't have many properties of the slime, is correct. Look, in these reference models, we don't simulate the interventions, the deep horizontal drains of the boreholes. I will come to that later. But in the reference models, also because they are hydromechanical models, we also get as an output the hydraulic conditions close, well, just before failure, say. And they are like these. You see in section 3, for instance, this is what you will call, it is not technically a water table, but it's the zero pressure contour, atmospheric pressure contour. And here, this is your unsaturated zone at the front of the dam. No? And well, here is the pore pressure before failure, and you can compute, extract values of those pore pressures and compare them with the readings of piezometers and CPTUs, and well, more or less, they were close to the readings. So that was, if you wish, a validation of the historical models. And also, well, you see, you have a bit of in this unsaturated zone here, you have a bit of suction, but not very much, yeah, about 50 kPa. And so now we have those, if you wish, calibrated models that seem to reproduce the history. And now we can do what-if scenarios. And one of them is, what if in the years after closure there had been a lot of rain, which it wasn't there, but just in case, what would have happened to the dam? Would have it failed just because of rain? Well, if it had rained a lot, the simulation says that the dam will have fully saturated. But that full saturation, in our model, and instability is not triggered. There is a bit of settlement, but nothing like what was observed. And what if the dam had been constituted by materials that could creep? Remember, we did measure if they could creep, and they cannot creep, but just in case. Well, if creep had been a feature, well, again, we will have seen delayed settlement here. I mean, the settlement that had taken place already was still will have been still taking place, but nothing really will have happened at the front of the dam. And also, if you go to the report, we do several hypotheses about that. If you mix a lot of rain and creep, nothing happened. The dam is still stable. By the way, and there is one issue with this introducing creep. And the issue is that if you really believe that tailings have creep, the problem is that when you apply a shock, a trigger, to something that has viscous properties that can creep, then the response to that trigger is delayed. So it is apparently stronger. So I cannot enter into that, but please look at this work that we have recently published on the analyzing mesh group. And large creep is favorable against sudden shocks, but Brumadinho didn't have creep. So it didn't have that safety valve against shocks. And what shocks? What were the triggers? Well, you know that in liquefaction analysis, we have two kinds of things. Susceptibility analysis, which is the thing that you do to identify if the condition of a deposit makes it potentially liquefiable, and we do that typically by looking at CPTU results. And then there is triggering analysis, which is that given the conditions on a deposit and given some event, is that going to actually fail? This one is more difficult. And you know that what is an event? Event is any kind of hydromechanical loading in this context. It can be an incremental load, a stage raise, say like, for instance, maybe in Fundão. It can be slope erosion, maybe like in Marisbrut. Overtopping, slope erosion, that is a trigger. Or it can be foundation failure, as in at Nalcoya. Or it can be a pore pressure increase, as it has happened in other circumstances, a raising water table, drainage malfunction. Well, you know, the problem with Brumadinho was that when we considered that catalog of possible triggers, we didn't find any that was likely. The dam had stopped being built 3 years ago. There were no earthquakes on that day. There was no rain on that day. There was no foundation failure. The water table was being lower. And there was, well, creep, I have already explained you that is not really a trigger. What about internal erosion? For several months, we were looking a lot at this photograph. In one report, 6 months before failure, it appeared that there might be a bit of internal erosion, but that was an isolated event, and weekly reports, week after week, didn't notice anything like that ever again. I think that was related to the issue of that failed drain installation, and there was no evidence really of internal erosion. So that wasn't that wasn't even an explanation. So what was then a possibility? Well, there was another report to Vale that was focusing on organizational events of the dam. But the people that did that report were very clever. And they said, well, you know what? We are not geotechnical specialists, and we cannot say why, but please take note that the drill that was operating on the day of the failure was suspiciously located right in the middle of the things that appear initially. And to be honest, I mean, we have completely discarded that idea, partly because the review, the initial review had presented some analysis to that effect, also because it did seem outlandish. How can a borehole trigger this thing, this terrible failure? But the more we knew about that borehole, the more suspicious it looked. Because you see, that borehole was being drilled here, and this is the water table. When we simulated the water table, you look at where the borehole is, and this borehole is being drilled with water. So you have the level of water here at the top. So that is a significant increase, localized, of pore pressure around the borehole. And when we compute the increase, well, it was significant, about 300 kPa. So the next step was to see, well, what happens around a material that now we have calibrated with CASM and is very fragile. And when you apply a sudden elevation of pore pressure around a borehole, that was a separate analysis. And when we did that kind of analysis, well, what came out was, well, that liquefaction took place around the borehole, about half a meter, 1 meter around the borehole, depending how impermeable your material is. The more impermeable, the better. And actually, when you look at the last borehole, where they were drilling in an area where there was a lot, 12 meters of this very, of the worst material that we have, of those CPTU fines. You see, there was another borehole drill with the same depth, the same water table increase previously but the conditions there were not so bad, because you see, you had like little drainage features here. So that was suspicious. Anyway, okay. So with all those ideas, we say, okay, we're going to test this. We weren't convinced, but we said, we're going to test this idea. We introduce here the geometry of the borehole, and in one small area around the borehole, 1 meter by 3 meters, we're going to tell that model, okay, now this has been liquefied by the drill. See what happens next. Because the failure is very fast, we simulate this drain. And you see, well, you have your localized failure there, and then, ooh, it comes out and it falls down, you see? You have your localization extends, and then you have this failure coming up, and this motion, the motion that appears there, is very much like the one you see in the videos. It is dominated by a vertical displacement here at the rear, and it has a main by a horizontal displacement here at the front. So it looks suspiciously similar with what was seen. And then, well, it's true that in those 2D plane strain simulations, the extent of the borehole is exaggerated in the out-of-plane direction, because a borehole is a 3D thing. So we did check if a 3D borehole will actually create the same effect in a slice of the dam. Note that 3D Plaxis, and we intend to do a 3D model of the whole dam at some point, but that is difficult, because, for instance, 3D Plaxis doesn't include currently rain, and 3D Plaxis that will have to deal with this geometry is a difficult thing. We did fail on creating the geometry, and we expect now to improve that with the help of Bentley. But on those slides model with the 3D borehole, you get exactly the same kind of failure when you trigger this small bit here, which is a small bit here, you fail the whole 15-meter slice of the dam. So that looks a likely explanation. And then we did also some checks. What happened in the previous borehole? If the previous borehole would have been triggered, well, you had some liquefaction, but it's contained. It doesn't create a massive failure. What about the deep horizontal drain? Well, because of how the materials are distributed, you have contained liquefaction. It doesn't propagate in the same way. So I'm finishing now, and that's enough of me. I was asked to extract some lessons about all this. I'm still thinking about them. I will say, well, some of them are pretty obvious, and I think that they have been already enforced in Brazil, which is that you shouldn't build dams with brittle liquefiable materials. Now, if you have to deal with a dam that is there already with this kind of materials, my view is that the first thing that you might need to think is about what are the consequences of failure if it takes place, and focus on mitigate consequence first, and then deal with reducing failure probability. And if you have to do any kind of intervention to reduce failure probability, however good or small, think it through and eventually do some triggering analysis. And if you're going to do triggering analysis, use critical state models. You don't need to use CASM. You can use NORSAN, for instance, or other models that are available. And also use coupled hydromechanical modeling. It's important to have coherence with the model that you use to build the dam and the one that you use for trigger, because that will give you confidence on the triggering thing. The triggering is a very delicate analysis. Another thing that I have learned from this is that mapping different, where in tailings you have sometimes the good, the bad, and the worst. and you need to, you need to locate where the bad is and the worst is, because that is what made a difference in our analysis to one section and the next one. And you might try to use the same link that we have shown to, between field and lab, using through permeability. And when testing in the lab, use reconstituted materials and use K-knot consolidation. And those are the lessons I have. And then I have a to-do list of the things that I will like to understand about these kind of problems, but I don't yet understand. It's, for instance, what will substitute a safety factor with this kind of analysis? Or if you can frame it more generally, where should we place material uncertainty? For instance, not in critical state friction. Yeah? That is very certain. There is very little uncertainty in that property. And where should we place geometric uncertainty? Maybe on trigger location, maybe on the distribution of materials. How are we going to do that? And then finally, I wonder many times, how unlucky was that done? How unlucky? And that's all for me. Thank you very much.
Okay, Dr. Marcos, thank you very much for your explanation. Thanks for your participation in Geotecnia Brasil. We really appreciate the presentation. Congratulations for your amazing job. Congratulations for your team and all the people. Okay, and now I would like to introduce the moderator for the questions and the answer sections. Professor Alberto Sayão, are you here?
Yes, yes, I am. Can you hear me?
Yes, yes. Dr. Sayão was a president of Brazilian Association of Soil Mechanics and Geotechnical Engineer from 2004 to 2008. Nowadays, he is a vice president of Brazilian Dam Committee. He is a professor of PUC Rio, Pontifical Catholic University of Rio de Janeiro, and he has a lot of experience in dam design and safety of dams, reliability, and risk approach. Dr. Sayão, thank you very much. And you can start your comments, your points, okay? Sayão is a consultant of Ministério Público. He has experience of Brumadinho dams. And now, please, Sayão, you can start your participation.
Ok, thank you. Tiago, eu vou pedir licença para falar em português, porque acho que a maioria dos nossos ouvintes vão entender. E eu peço desculpas ao professor Marcos Arroio.
Não, me faz prazer.
Vou falar devagar, um portunhol brasileiro, para você poder acompanhar. Primeiramente, eu queria agradecer não só o convite da Geotecnia Brasil para participar desse evento, muito importante na semana que nós temos 3 anos do desastre. E eu queria, então, comentar sobre a bastante detalhada palestra do professor Arroio sobre as análises computacionais e também os resultados experimentais que ele apresentou. Muito obrigado, Arroio. Você conseguiu resumir o extenso relatório que você e seus colegas da Universidade Politécnica da Catalunha apresentaram para o Ministério Público, juntamente com a participação do professor Antônio Viana da Fonseca, da Universidade do Porto. Então, foi uma vamos dizer, um grupo internacional contratado pelo Ministério Público Federal do Brasil e o objetivo era fazer análises numéricas sobre as causas do acidente que já tinham sido comentadas no relatório do professor Peter Robertson e colaboradores, como o próprio Marcos Arroio nos mencionou no início. A minha função, juntamente com o professor Terzariol, foi acompanhar os trabalhos da equipe da Catalunha e poder comentar ou traduzir, entre aspas, para o Ministério Público do ponto de vista do trabalho chegar a conclusões importantes. Eu recebi aqui, enquanto o professor Arroio fazia a explanação, eu recebi aqui mais do que 15 perguntas e eu selecionei rapidamente as principais, porque não sei se nós teremos tempo de fazer todas as perguntas. Então, eu vou começar por uma visão geral, uma pergunta geral para o professor Marcos Arroio. Marcos, qual é a sua opinião sobre as upstream dams, quer dizer, as barragens para, como é que vocês falam? Águas arriba, né? Qual é a sua opinião? Você acha que elas devem ser proibidas, como já o é no Brasil, ou você tem alguma opinión diferente?
Bueno, yo, aprovechando que habla en portugués, me voy a pasar al castellano.
Está bien.
Bueno. A este respecto, creo que la medida que han tomado en Brasil es adecuada para las condiciones de Brasil. Un país con una pluviometría muy significativa. No estoy tan seguro que una prohibición absoluta sea también necesaria en países desérticos, por ejemplo, porque en países desérticos es posible que las condiciones de saturación de los relaves sean más favorables. Aún así, es verdad que yo creo que lo que es difícil de estas presas no es el proyecto. Las ideas para hacer un proyecto bueno, yo creo que están claras desde hace ya décadas. El problema es la construcción y el control. Y entonces, claro, aunque uno pueda decir, no, en principio se pueden proyectar, quizá llega un momento en el que la profesión tiene que reconocer que, aunque en principio, en condiciones ideales, se podrían hacer para que no pasaran problemas, en la práctica está resultando tan difícil que no vale la pena seguir intentándolo.
Claro, ok. Vamos passar uma breve discussão sobre esse ponto, porque eu acho que é de grande relevância e interesse para todos. As barragens para montante, upstream dams, no Brasil foram proibidas muito rapidamente, pouco depois do desastre de Brumadinho, que eu acho que foi uma decisão muito rápida, importante, mas muito rápida, no sentido de dar à população brasileira, já bastante preocupada com as barragens de rejeito, dar uma satisfação, porque esse foi, como você sabe, o segundo evento 4 anos depois da tragédia da barragem lá em Mariana, que foi a barragem do Fundão. Então, eu creio que a Agência Nacional de Mineração precisava mostrar que alguma coisa tinha que ser feita, mesmo que sendo bastante drástica, para evitar novos acidentes como esse. E aí houve a proibição. Porém, do outro lado, o Brasil tem muita experiência com barragens de rejeito, com barragens em geral. Engenharia de barragens no Brasil é reconhecida como de boa qualidade. E, portanto, eu acho que faltou um pouco de conversa com as entidades de engenharia para podermos ver que tipo de sugestão poderia ser feita para continuar a executar barragens para montante que são conhecidamente mais econômicas, porém mais perigosas. Quer dizer, que tipo? Eu teria várias sugestões sobre como fazer as barragens para montante de maneira mais segura, mas não vou me estender aqui, porque o objetivo é nós comentarmos as perguntas sobre a sua análise, sobre a sua charla, palestra de hoje. Então, além disso, outra pergunta. Para as barragens para montantes já existentes e, eventualmente, já desativadas, como era o caso da barragem B1 em Brumadinho, que tipo de sistema de monitoramento você recomendaria? Ou seja, que instrumentos você acha importantes que sejam especificados ou garantidos na barragem paralisada?
A ver, sigo en castellano. La instrumentación, los instrumentos están para responder a una pregunta. Los instrumentos los ponemos para que nos informen de algo y para poder actuar en consecuencia. Yo creo que ahora mismo no, o sea, si no hay instrumentación posible para avisar de una rotura tan rápida como estas que se pueden dar. Entonces, ese no puede ser el objetivo de la instrumentación. La instrumentación no puede plantearse como con eso voy a tener tiempo de respuesta. Nunca se va a tener. El objetivo de la instrumentación debe ser otro. Debe ser vigilar que las condiciones que hacen que una estructura pueda liquefactar no se dan. Entonces debe ser instrumentación que se interpreta para decir, si se ha depositado material malo, pero tiene que ser que se pueda actuar. Es decir, si se ha depositado material malo y la instrumentación me lo dice porque veo presiones de poro más elevadas, porque los desplazamientos indican una compactación mayor o lo que sea, pero si se ve eso, ¿qué se hace? Esa es la pregunta. Hay instrumentación para detectar eso, pero la cuestión es, si se detecta, ¿cuál es la acción subsiguiente? Y la acción tiene que ser fuerte, tiene que ser que se paraliza el depósito en el momento que se detecta un fallo, en la construcción. O sea, si la instrumentación nos sirve para hacer algo, la instrumentación nos sirve.
Sim, claro. Eu creio que a pergunta talvez estivesse dirigida para a necessidade de termos instrumentação automatizada e talvez até um plano de emergência, um alarme automatizado também. porque no caso de Brumadinho,
sí, a ver,
não houve tempo para se ativar um aviso de alarme para as pessoas poderem sair da região
a ver,
ajusante da
Sayao,
barragem. Pois não.
en una de las lecciones que yo ponía es que, para mi gusto, una de las lecciones principal es que si se identifica una situación de riesgo, como sabemos, es el producto de dos cosas, de la probabilidad de fallo y de la consecuencia del fallo. En este tipo de presas, donde si se identifica una posibilidad de riesgo, donde hay que hacer la ingeniería inmediatamente y donde hay que reaccionar es en la consecuencia. O sea, es en no tener, en minimizar el impacto. Y luego ya pensaremos en bajar la posibilidad de rotura.
Muito bem, eu concordo plenamente. Professor Marcos Arroio, eu vou aproveitar então, e já que você falou em probabilidade de falha, vou passar a uma pergunta sobre o assunto, sobre o tema. Qual seria o valor aceitável do parâmetro beta, que é um parâmetro ligado à variabilidade, né? À incerteza?
Sim, da fiabilidade.
Exatamente, exatamente. Qual é o valor aceitável de beta, ou, em outras palavras, qual o valor aceitável de risco de ruptura ou risco de falha? Como que nós podemos definir isso para projetos de barragem de rejeito?
Bueno, pues Sayao, ahí me ha pillado porque no soy un especialista en fiabilidad, pero la fiabilidad de un proyecto debe estar ligada al riesgo que importa. Esto es la idea que yo tengo del análisis de riesgo. Si el impacto del fallo es muy significativo, la fiabilidad que se exige al proyecto debe ser mayor, claro.
Claro, claro. Isso aí é uma pergunta realmente bastante detalhada sobre a probabilidade de falha, que é diretamente dependente do parâmetro beta.
Sim,
Mas
sim.
não vem ao caso, então. Eu diria que isso é preciso ter muito mais experiência e muito mais casos avaliados. No caso de Brumadinho, a probabilidade de ruptura avaliada era da ordem de 1 para 4,5. Quer dizer, um valor bastante alto de probabilidade de falha. Eu não vou entrar em detalhes aqui, só queria que você comentasse.
Si me permite, ahí, al hilo de esta observación, cuando yo ponía este tipo de análisis que hemos hecho, que se ha hecho varias veces, se hizo en Fundao, se ha hecho y está pasando a ser una herramienta de proyecto y de cálculo, ¿no? Sí. Y aquí lo que no está maduro, creo yo, es precisamente la perspectiva de fiabilidad. Porque para poder derivar una fiabilidad, ¿cómo de fiable es este análisis? Tenemos que focalizar en las incertidumbres de entrada del análisis, que serán las que luego dicten la fiabilidad del análisis. Y hay incertidumbres tanto en la definición del material como en la definición geométrica, como en la definición de las acciones. Porque, por ejemplo, está muy tratado, y yo creo que se entiende relativamente bien cómo definir la acción sísmica. Pero cómo definir la acción que podríamos llamar gatillo, yo creo que no está aún pensado desde una perspectiva como la que usted plantea. Entonces, creo que hay mucha labor por delante para poder poner este tipo de análisis en medida de dar respuesta a su cuestión.
Perfeito. Marcos, vamos mudar então para outros temas. Nós tivemos perguntas sobre a a parte experimental de campo e também sobre a parte das análises numéricas. Então, vamos falar sobre a parte experimental. No campo, a pergunta é, ao invés de usar CPT, Cone Penetration Test, você recomendaria também o uso do DMT, Marquette Dilatometer? Como que você recomenda? Qual é a ferramenta mais confiável?
No, a ver, yo recomiendo hacer las dos cosas. Y yo recomiendo además que se hagan alguno de ellos que tenga además el módulo sísmico. El precio de estos ensayos comparado con la información que dan cualquiera de ellos es minúsculo. Hay que hacer mucho CPTU y hay que hacer mucho marketing, las dos cosas.
Sim, o CPTU tem a vantagem de poder ter as medidas sísmicas, então seria o Seismic Cone.
El marketing también.
Também, mas
También.
A desvantagem do CPT, no caso, é o problema da velocidade de penetração. O problema de rate effects. No caso de uma argila ou de um solo fino, como no caso dos rejeitos de Brumadinho, que poderiam ser sujeitos ao efeito de velocidades diferentes. Esse assunto está em pesquisa. O professor Fernando Schneider, aqui do Brasil, tem trabalhado sobre isso e creio que em breve nós teremos resposta sobre esses efeitos para poder compartilhar com todos. Vamos, então, você quer comentar alguma coisa a mais ou vamos passar para a parte do triaxial, ensaio de laboratório?
Al respecto de esto, que tiene mucha razón, quiero comentar que efectivamente para nosotros un aspecto muy útil fue poder contar con la capacidad de simular el ensayo in situ con el mismo modelo constitutivo que usamos para representar la presa, porque esto nos permite conectar y entender mejor la información del ensayo in situ. Eso es verdad que eso, como decía, ahora mismo no está ya en praxis, pero yo creo que estará. Si los conozco bien a los de Bentley, pues en un año o dos seguro lo tienen. O sea que eso yo creo que es una idea que conviene tener presente, que es útil.
Perfeito. Já que você falou nas análises em Praxis, tem uma pergunta sobre isso, que é: please comment on the use of 2D or 3D models for dams analysis.
Okay, well, I will answer to that in English because the question is in English. The comment is 2D or 3D. I think that the question is not 2D or 3D. The model needs to be useful to answer some. It's like instrumentation. You need to have something that is useful for a purpose. And in some circumstances, you will absolutely need to do a 3D analysis. But in other circumstances, a 2D analysis will give you enough insight on what is going on. In Brumadinho, we plan now that we have more or less identified one likely culprit to do a full 3D analysis with Bentley. That won't be easy because you see, I think you need to understand that the trigger is 1 cubic meter in a failure that was 9 million cubic meters. That will give you an idea of the scale of the mesh that you need to create to sort of simulate that. So I think that that will be an interesting exercise, and I am looking forward to work with Bentley on that. But you cannot say 3D is superior to 2D. A model is something that you do with a purpose. If it gives you insight, that is the purpose of the model.
Ok. Vamos, então, para o próximo assunto, que é a parte de laboratório. E o assunto é Specimen Preparation, já que você mostrou aí alguns ensaios terciais realizados na Universidade do Porto. A pergunta sobre a preparação dos espécimens, dos corpos de prova, deve-se usar o moist stamping, no caso de reconstituted specimens, ou deve-se usar o slurry deposition method? Ou você prefere, como foi o caso que você mencionou, usar amostras indeformadas, undisturbed specimens?
Well, again, I think that as it is practiced now in the lab, the best way is reconstituted moist stamping. It is true that slurry deposition looks more like what happens in the field, but then for some reason they don't seem to get it right in the lab. So, and I think that with moist stamping they get results that then when you plug it in the models, they seem more like what happens in the field. And then there is the other thing about the fact that in the field you have all this layering that will appear, but you cannot test that in the lab. I mean, you can test that in the lab, but the moment you introduce that variable, you have just too many variants. How many layers? Which materials? I mean, it just becomes too complicated. And again, as numerical modeling, you do lab within your means to get some cues to help you understand the problem. There is no foolproof method always. I mean, it is yeah, I think that my bet now is moist stamping reconstituted. But,
Ok. No caso das amostras utilizadas para esse estudo, elas foram undisturbed, mas não exatamente undisturbed. Elas foram o que era possível se obter numa região do depósito que não tinha sido movimentada pelo acidente. E aí, naquela região, eu sei porque eu estive lá com o pessoal da Polícia Federal e vi o local e a metodologia de extração da amostra. Do ponto de vista puramente acadêmico, ela não era indeformada, porém, era o que era prático, né? Era o que era possível se fazer. E desse ponto, eu creio que foi muito bem sucedido. Muito bem. Então, vamos passar para as main lessons do grande acidente de Brumadinho, que, infelizmente, vitimou 300 pessoas, aproximadamente. Bom, as main lessons, no caso do relatório dos internacionais Peter Robertson e colaboradores, as principais causas, segundo eles, foram: a barragem era uma barragem upstream. Segundo, a inclinação da face da barragem era muito acentuada. Terceiro, que é um assunto que você já comentou, a perda da sucção devido às intensas chuvas que ocorreram nas semanas anteriores ao colapso. Então, essas foram as principais causas, segundo o Peter Robertson. Você comentou que a sucção e o problema do creep talvez não sejam tão importantes como o Peter Robertson concluiu no relatório. Você pode comentar alguma coisa a mais sobre isso?
Sí, a ver, nuestra opinión, lo que de momento resulta, bueno, respecto al creep, hay varias razones. La primera es que en el laboratorio no se ve viscosidad. Y entonces, quiero decir, ya, segundo, que de la naturaleza del material, no plástico, granular, etcétera, no hay una razón física obvia por la cual uno pueda imaginar un mecanismo viscoso. Y tercero, que, y eso lo descubrimos después, que si hubiera sido viscoso, o sea, un material que es viscoso tiene un amortiguador. Y entonces, cuando tiene un shock, el amortiguador para el golpe y puede romper más tarde. Pero el efecto inicial es parar el golpe. Entonces, digamos que lo del creep me parece que no estuvo acertado en ese aspecto el panel y que no es una idea que tenga interés en tailing. Otra cosa es en slimes, donde hay arcilla, donde hay plasticidad para la consolidación. Ahí sí que puede haber creep. Pero en tailings, en estos, yo creo que ahí nos miraríamos en la dirección equivocada. La segunda cuestión es el tema de la succión. La succión, efectivamente, no es una cuestión trivial. Pero en las condiciones concretas de Brumadinho, nos parece que fue un efecto completamente secundario, aparte de que probablemente no presente, puesto que no fue como este mes que han tenido ese diluvio universal en Minas Gerais. No fue así hace 3 años. Entonces, y yo creo que es importante resaltar esto, porque si la conclusión es que las presas ya existentes, primero, están fluyendo y segundo, si llueve mucho se van a caer, a lo que conduce eso es a tener que intervenir lo más rápido posible, porque son un peligro inminente. En cambio, si la situación realmente no es esa, más bien nuestra conclusión es la opuesta, es que efectivamente hay que reducir el riesgo, pero primero tiene que actuar sobre la consecuencia. Y segundo, a la hora de reducir el riesgo, vaya usted con mucho cuidado, porque a lo mejor, o sea, si es frágil, cualquier detonador puede romper.
Claro, e o Peter Robertson menciona que a fragilidade do depósito de tailings era devido à cimentação com óxido de ferro, que era presente nos rejeitos. Isso aí é bem possível, é uma explicação possível, mas eu não sei se o material teve tempo suficiente e nem fluxo ou percolação suficiente para haver esse tipo de deposição de óxido de ferro nos contatos entre as partículas dos rejeitos. Você consegue entender o meu português?
Lo he entendido perfectamente, Alberto.
Ok.
Y
Entonces,
además, bueno, sobre ese particular, me gustaría, además, hay muchas razones por las cuales yo creo que también ahí, en ese aspecto, no fue una idea fértil, más bien fue una idea errónea y que no se debe seguir. Pero algunas de las razones, me gustaría hacer más ensayos sobre material de Brumadinho. ¿Me puede enviar un poco, si se lo pido? Ya que estamos aquí. porque hay unos ensayos nuevos que me gustaría hacer para probar de forma aún más evidente el aspecto este de que la fragilidad que vieron que había algunos aspectos que decían eso, parece que puede estar ligada a la sistemática de compactación que emplearon. Y ese es un aspecto que se podría probar en laboratorio y que me gustaría ensayar. Si logro tener o sea, que si pasa cerca de la presa, pues, hombre.
Sim, claro. Agora, Marcos, retornando ao assunto CRIP, que foi um dos pontos muito ressaltados pelo Peter Robertson. Eu concordo que não é uma coisa fácil de se aceitar como sendo a principal causa. Mas eu acho que a razão é a seguinte: nós sabemos que, nas vésperas do acidente, estavam sendo feitas perfurações para a instalação de instrumentos, piezômetros e inclinômetros, como você mencionou. Essas perfurações deixam vazios dentro da massa de rejeitos. E isso, com o tempo, a tendência é o furo fechar, porque ficou vazio, e então isso aí vai causar uma movimentação na massa que seria talvez a causa primária da movimentação devido à CRIP. Eu não sei se isso é uma coisa bastante aceitável, mas gostaria de ouvir a sua opinião sobre isso.
La evidencia que presenta el panel sobre movimientos que ellos identifican como CRIP es una evidencia basada en estudios INSA.
Sí.
Mi impresión, después de haber mirado sus estudios y los de los demás, es que en los movimientos de la cara de la presa hay demasiada incertidumbre como para dar credibilidad a ese INSA. Me gustaría que alguien hiciera la comparación. Todos esos INSAR además se han hecho sin tener en cuenta todas esas actividades que usted describe. Probablemente no tienen la resolución adecuada, porque el INSAR, como sabe, pasaba una vez cada 15 días.
Claro,
entonces, probablemente no tengan la resolución temporal adecuada para poder ver estos efectos de sondeos y de tal. Pero ese es un estudio pendiente y que yo creo que vale la pena hacer. Integrar las actividades que hubo en eso con esas observaciones.
Sim. Aqui mesmo no Brasil, há estudos sobre a utilização das medidas de satélite em barragens. Esses estudos estão sendo realizados atualmente sob a orientação do professor Pedrito Rocha Filho. Mas não vamos entrar em detalhes aqui. Eu queria voltar, então, à conclusão. Eu acho que, do que nós discutimos aqui, podemos dizer que, agora é a minha opinião, que num depósito de rejeitos com um elevado grau de saturação, praticamente saturados, não devemos fazer perfurações, principalmente com pressão de água, quer dizer, com água pressurizada, para fazer instalação de instrumentos. É uma ação de perigo que eu acho que deve ser uma lição aprendida.
Sim.
Não sei se você gostaria de comentar sobre isso. Agora, por que o material estava tão saturado? Porque houve evidências de não ter funcionado muito bem o sistema de drenagem da barragem B1. Aliás, isso aconteceu também com a barragem de Fundão, lá no caso de Mariana. Problemas nos sistemas de drenagem das barragens de rejeitos. Então, essa é uma segunda lição, a meu ver. Precisa muita atenção na hora da construção e depois na hora da utilização dos sistemas de drenagem. Se o sistema de drenagem mostrar dificuldades na drenagem, como foi o caso de Brumadinho e de Mariana, então é preciso acender um alerta para que não ocorra esse tipo de ruptura súbita, repentina, que nós observamos nos dois casos. Não sei se você pode comentar, pode discordar ou completar o que eu falei, por favor.
No, estoy bastante de acuerdo. Respecto a los sondeos, efectivamente, yo creo que, claro, quizá había una desproporción ahí que era difícil pensar en eso, ¿no? Pero es cierto, aunque el mecanismo de rotura es distinto, sabe usted bien que en las presas de núcleo de arcilla compactada se prohíbe usar el agua en las perforaciones para que no haya fractura. Aquí no fracturamos, aquí lo que tenemos es una onda de licuefacción, que es un mecanismo distinto. Pero es verdad que en esas otras presas se ha prohibido y hay otros mecanismos de sondear. Entonces, yo creo que desde luego se debe prestar mucha más atención al sondeo, por lo menos registrando, o sea, si estás en esas circunstancias, registrando los parámetros, poniendo controles en la presión, etc. O sea, eso estoy completamente de acuerdo. Y respecto a la otra cuestión que decía, que era el tema del drenaje, pues sí, yo creo que es posible, aunque eso desde luego no lo he investigado en detalle, que en este tipo de... O sea, el problema del drenaje en las presas de relaves es que la geoquímica es muy compleja. Entonces, tenemos materiales que sin llegar a tener bonding, sí que pueden segregar, crear óxidos, hacer depósitos, particularmente en zonas en las que están expuestos a la interacción con la atmósfera, ¿no? Y esas costras, esas cosas pueden perjudicar el drenaje como se plantea. Entonces, esos son aspectos que desde luego, pues yo creo que de los más complejos que tiene proyectar un drenaje. No es lo mismo proyectar un drenaje en una escollera de granito que en algo que en un material de química un poco brava, ¿no? Como es el caso de los tailing.
Sim. Muito bem, Marcos. Então, para completar lições, eu gostaria de voltar ao assunto da barragem para montante, águas arriba, que foi proibida no Brasil, e ela, aqui na América Latina, os países que também proíbem isso são o Chile e o Peru, onde não são feitas mais barragens para montante. Mas há países com grande tradição em construção de barragens de relaves, de rejeitos, que ainda usam isso, como a Austrália e a África do Sul. Então, quando eu falei que houve uma decisão para dar uma justificativa à sociedade, talvez em discussões com a engenharia surgiram soluções. Uma, por exemplo, que eu não sei se você concordaria, em vez de fazer a drenagem em direção à presa, à barragem, a drenagem deve ser feita para montante, para a parte mais arriba do reservatório. Por quê? Como seria? Fazer lá na extremidade do reservatório perfurações drenantes. E aí o fluxo, em vez de ir em direção ao sistema de drenagem na presa, na cara interna da presa, o fluxo iria para o outro lado, evitando qualquer tipo de ação de liquefação ou de piping na barragem. Não sei se você entendeu essa ideia e se você concorda.
Bueno, alguna ventaja, claro, parece que tiene, ¿no? También yo creo que la cuestión, porque o sea, el drenaje está para garantizar condiciones de no saturación en un buen núcleo,
Sim.
en un núcleo estructural. Entonces, pero, insisto, como idea es buena, pero también si recordamos el caso o hasta donde lo conozco yo, el caso de Fundao. En Fundao había un proyecto que era bueno, pero luego por imponderables de construcción, entre otras cosas, el drenaje que estaba bien planteado no tuvo lugar.
Isso.
Entonces, insisto, el problema no es que no tengamos las ideas claras sobre qué es lo que habría que hacer. El problema es más de otra índole, es que el sistema de control que se creó no tenía las condiciones efectivas para imponer tal. Eso sin contar ya con el legado de las que están mal hechas, ¿no? Entonces, yo creo que la discusión no es en cuanto a que no tengamos capacidad de concebir una presa aguas arriba que sea efectivamente segura. Yo creo que es más bien de índole organizativa y de tal. Y en ese aspecto, claro, es donde tienen ustedes un trabajo, bueno, pues más complejo a la hora de convencer a los reguladores de que las cosas han cambiado, ¿no? Pero yo creo que si alguien les podrá convencer será la gente de Geotecnia Brasil.
Sim, com certeza. Marcos, muito obrigado. Eu acho que nós podemos encerrar, porque já passamos de 2 horas. Você deve estar cansado. Nós precisamos, para encerrar, fazer 2 coisas. Primeiro, agradecer. Segundo, pedir desculpas pelo fato de ter feito não uma discussão, mas quase que um interrogatório com você. Aí eu peço desculpas, a culpa é minha. Agora, para os agradecimentos finais, já temos aí o nosso coordenador do Geotecnia Brasil, professor Tiago Souza. Por favor, Tiago, fazer os agradecimentos finais. Peço desculpas pelo longo tempo que nós ficamos aqui.
Gracias.
Ok, professor Sayão. Eu vou fazer os agradecimentos em português, já que os formalismos foram quebrados, mas em respeito ao palestrante, eu vou também tentar fazer os agradecimentos em espanhol, tá bom? Então, em nome do canal e grupo Geotecnia Brasil, eu agradeço ao Dr. Marcos pela brilhante palestra, agradeço muito todo o compartilhamento. Essa é uma live histórica, porque tivemos não só a palestra, mas uma sessão técnica rica e produtiva. Eu quero também lembrar aos colegas que o professor Marcos fez uma palestra sobre o mesmo tema em Calgary, para a comunidade geotécnica de Calgary, e a diferença do evento dos canadenses para o nosso é que, além da palestra, tivemos aí uma sessão de perguntas e respostas, o que engrandece o nosso trabalho aqui, tá? Dr. Marcos, muitas gracias. Tuvimos uma secção muito rica e produtiva. A interação Brasil-Espanha com você e com o professor Sayão foi excelente. E gracias, Dr. Marcos, de novo, por sua atenção.
Muchas gracias a vosotros y a Geotecnia Brasil. Ha sido un verdadero honor estar con vosotros hoy.
Obrigado.
Um abraço, hasta pronto. Tchau.
Adiós.
Saúde.